Well, good morning, grade 12s. All right, so welcome to your new video. I know how much you love my videos, so I'm now making you another video this morning. And in this video, I'm going to explain how to do a few more centripetal motion questions, because this will be the subject of our next quiz. And we did discuss today that our next quiz will be next week, okay? Now for cohort B, I'm going to see you tomorrow. So the next quiz will be on centripetal motion, and it will be on Tuesday for you, okay? So we're going to cover all this. We're going to go over these questions, and we'll have time. I guess you're not watching this video, but I'll tell you about this tomorrow. And we said for cohort A, it would be on Wednesday next week, and it'll be strictly on circular motion questions, like the ones that we're going to look at here in a moment. All right, so today I showed you, or I guess it's now yesterday for you, I showed you how to do problems with the pendulum, so the vertical pendulum and the conical pendulum. Let me now show you how to do one that involves a roller coaster. Okay, so here we see this roller coaster here, and it's sort of a loop-de-loop. You can see the kids having fun. Pandemic, those were the days before the pandemic when we could go to Canada's Wonderland. All right, so here the people are upside down. They don't fall off the track. Of course, the roller coaster is sort of, switch colors here. The roller coaster is, going around this way. And yeah, so what kind of question could you get about roller coasters? Well, let me give you an example. I'm going to assume our little friend here with the hands up in the air is about 2 meters from the base of the track, okay? So like here's the base of the track that they're sitting on. I'm going to assume that that color that I've just colored in sort of dark there, it's about 2 meters. So I'm trying to count what the radius is here. 2, 4, 6. Let's say that this is I'm going to erase what I just did there. Let's say that the radius here is approximately 7 meters. Okay, so we'll go with a 7-meter radius track. Now I have a question for you. Okay, if it's a 7-meter radius track, so here's a typical question. When they're upside down here, let's say that they just lose contact. Okay, now what do I mean by that? I don't mean that they're about to die. Okay, I don't mean that. I mean that their bums feel like they're coming off their seats because they're upside down. Now, they're not actually going to fall out of their seats, but they're just starting to fall out, okay? This would be a kind of question like if you had a bucket of water and you were sort of spinning it upside down, and the water almost falls down, all falls out at the top when it's upside down, but not quite. And if you get the circular motion just right, that's what happens. Okay, so you're just about to lose contact. My question for you is, what's the speed at this point? Okay, so sure, they're moving around the track with speed v. So we would call this the minimum speed not to fall out. Let's say somebody forgot to buckle them in, but they won't fall out at this minimum speed. Okay, what is that minimum speed? Let's find out. Okay, so what we're going to do is we're going to draw a free body diagram here. I'll use a little highlighter here. Maybe does it come out? No, it doesn't work very well. Let me use a rainbow color. We're going to draw a free body diagram of someone that's right here in the totally upside down position. Okay, what does their free body diagram look like? I mean someone sitting on the seat. Okay, so a free body diagram at the top of the track. What does it look like? Well, pretty straightforward, really. Here's our cart, or here's the person, let's say. Gravity is down. It's always down. Okay, never put gravity any other direction but down. But there's another force here. The only thing touching them is their seat. Now, that would be a normal force. That would also be down, because after all, the seat they're sitting on is upside down, right? You're upside down sitting on a chair. So yeah, your bum is touching the chair, but you're upside down. So that chair can only push on you, and it can only push you down. Now, if you had a seat belt, it could hoist you up, okay? So you always wear a seatbelt just in case, okay, that's for safety reasons. But that's the free body diagram. Now here's the deal. Those are the only two forces. Now I'll put the velocity in here. I know this is a bit unusual to put a velocity in this. They are moving this way at this particular instant, but that is the tangential, I'll put VT, that's the tangential velocity. Here, you know what, I'm gonna zoom in a little because I'm having a hard time. So that's the tangential velocity. So yes, they are moving, okay? And that's why they don't fall out. But the deal is, if there's no other forces acting on this person, they must be accelerating. And of course they are, with radial acceleration. See, you always accelerate. When you're moving in a circle, you're always accelerating towards the center. So here, the center, when you're at the top, is right below you. Okay, here's the center of the circle right there, but it's right below the rider when they're at the very top of the circle. So you always put the centripetal acceleration, or the radial acceleration as I like to call it, towards the center of the circle. Okay, now that's all, surprisingly. Okay, here you are in the roller coaster and that's all there is. So we only have a y component to worry about. We're going to make down positive because after all, everything's down in this question. And you get this, that the net force is equal to Fn plus Fg. So MAR equals Fn plus Mg. Now, at the minimum speed, you're just losing contact, okay? You're just losing contact. Well, this force here, this normal force, is the contact. But since you're losing contact at the minimum speed, the contact is equal to 0. In other words, your bum is coming off your seat. So the normal force will drop to 0. So that means this one is 0. And you get MAR equals Mg. Well, that's pretty easy. Now your mass cancels out. So it doesn't matter who the rider is. Okay, they'll have the same minimum speed. Okay. Now here, because it's circular motion, get used to it. AR equals V squared over R. Okay, this is our special equation for the radial acceleration that we're going to use in circular motion questions. So I'm going to say therefore V squared over R equals G, or simply V squared equals RG. Now I'm going to go ahead and solve it for V. V will equal the square root, R is 7, G is 9.8. Okay, take out your calculator. 7 times 9.8 is 68.6. Take the square root, I get 8.28 meters per second squared. Oh, I'm sorry. Yeah, meters per second, pardon me. It's a velocity. It's a speed. So 8.28 meters per second. Now, if you, in case you're curious, that's about 30 kilometers per hour. So the roller coaster has to be going around 30 kilometers per hour minimum speed so that no one, even if they weren't buckled in, they would not fall out of their seat, okay, at this particular rate of motion. Now, if they go slower, if you're going slower than 8.28, now what's going to happen is if you're not buckled in, you're falling out because you do not have enough speed to have the right radial acceleration for you to stay in your seat, okay? Like this is the falling out point. You can't go slower than that. So this is the minimum speed so that no one falls out. Now, if you go faster than that, and let's do another question now. So right next to this, we're going to get a completely new question. Let's increase the speed. Let's say we're going way faster than we need to. Let's say we're going 60 kilometers per hour, twice as fast, okay, as we need to go here. At 60 kilometers per hour, what will be the normal force? Okay, on the person. So sometimes you get a question like they're sitting on a scale. What will the scale say? Well, the scale reads the normal force. So let's go ahead and do it. It's the same free body diagram. So let's go straight to our y component. The net force, as we wrote before, is Fn plus Fg. Whoops, what happened there? Fn plus Fg. Okay, so now the Fn is not 0. We're wondering what the Fn is, but we're going to go MAR equals Fn plus mg. And then I'm going to substitute AR. I'm going to write V squared over R. Okay, so mv squared over R equals, oh, sorry, let me rearrange it. Minus mg equals Fn. Now I realize now that if I'm going to give you this question, I have to give you the mass of the rider. So let's say the mass of the rider is, I don't know, 50 kilograms. Okay, so now we'll plug those numbers in. What's this? Yeah, sorry. So we got 60 kilometers per hour for the speed. We're going to need to convert that to meters per second. So V will equal 60 divided by 3.6. So let's go ahead and do that. 60 divided by 3.6 is 16.7. So this is 16.7 meters per second. Now we've got everything we need. It's going to be 50 times 16.7 squared divided by 7 minus 50 times 9.8 equals Fn. All right, so let's square that speed, times it by 50, divided by 7, and then we'll subtract 50 times 9.8. I get 1494 newtons, which is extremely high. But anyway, so you end up getting, this is, now the person's going to get crushed because they're going too fast. You get too much acceleration. Anyway, you end up getting that Fn is equal to 1494. I feel like repeating that calculation. Let me just do that for a second just to make sure. So 50 times 16.7 squared equals, divided by 7 mv squared over r, right? Minus, now I think I did it right, 50 times 9.8, yep. Oh, yeah, okay. 1,494 newtons. That's a lot. They're going to feel like 3 times their weight. Now, you could withstand that. You're not going to pass out. You're sitting in a seat. You might want to brace yourself, okay? So the person weighs about 500 newtons, so that's about 3 times. They're going to, the scale will read 3 times their weight. So, you know, you're going to feel pretty heavy sitting in the seat, but you're whipping around that loop at a very high rate of speed, and you get that as your normal force. So that's how you do roller coaster problems. Pretty easy, right? No problem. Okay, so now another ride that they used to have back in the days when they had like the Super X at Lansdowne Park, which was like a, you know, I think now they do it at the Rideau Carleton Raceway. They used to have this ride called the Gravitron. And the Gravitron, okay, was a ride that looked like this. There's actually an operator in the center, and it's got this axis of rotation, and it would spin you around as you see here. It's like you're in a big cup with slanted walls, okay? Now, in this particular thing here, they show you like a coefficient of friction. We're not going to make it too complicated. This omega here, this is a lowercase omega, means the rate of rotation, like the angular velocity it's called, and it's usually measured in radians per second, which I think you learn about radians somewhere in your life in math. Okay, but anyway, yeah, forget about all that. We don't need all that, but we do need this angle theta here. Okay, so that's the tilt of the back wall. Now, if you actually went on this ride, they would spin you around. So you're sort of spinning around, you know, going around this horizontal circle like that. And then you'd be stuck to the wall. And in fact, the panels on the wall would slide upwards like this. Okay, and then you'd sort of, your feet would lose contact with the floor. Okay, but there was no friction because the sliding panels were on rollers. So it's just once it sped up fast enough, you would actually be stuck to the wall there. Okay, and yeah, so you know, if it stopped turning, you would slide back down. Okay, so there's no friction that holds you in place. So what's going on? Okay, well, this is one of those things where we draw a free body diagram. I'm going to say like here's their axis of rotation is this dotted line. So this is the spin axis, if you like. And the radius of the circle the guy is making is given by little r here. Let's say little r is, I don't know, 3 meters. Just making it up. That's about the size of that ride. It's about 6 meters in diameter, and there'd be people all around the outside. Like there'd be someone on the other side too, right? Okay, sitting over here. I know it looks like a little mini person there, but anyway, they're all people lined up all around this thing. It's not drawn to scale here. So the scale is a little bit larger than what you see here. The man looks quite large compared to the cup itself, but you could probably fit about 20 people in there. So picture it a little bit larger, but I'm going to say it's 3 meters. Okay. And let's say this angle theta here is 15 degrees. So let's say the angle here, this angle here, theta is 15 degrees. Okay. Now, given that information, how fast does it have to spin so that the guy doesn't slide down the wall? Okay. So what is again, the minimum speed? So he doesn't slide down. Okay. So he stays on the wall. Okay, on the banked wall. Okay, so this is a great question. Let's draw a free body diagram of the guy. See, again, like once you know how to do one circular motion problem, I mean, really it's all the same. So free body diagram of the guy, I'm going to tilt him a little like this. Okay, now let's see if we can work this out. We've got gravity, and gravity would be straight down on him. And there's also a normal force, and the normal force would be, here's my wall, kind of, okay? So the normal force would be perpendicular to that. It's like this, okay? Here we have at the base, I'm trying to understand my geometry here. Just hang on a second. So we know that the tilt angle, it's a line straight down. So we know that this angle here is 15 degrees. That's this angle, it's 15. But I want to get a different angle, and I'll show you why in a second. I'm going to have an axis that's horizontal and an axis that's vertical. So if that's 15, it means that this angle here would be 75 degrees, because 75 plus 15 is 90, right? And that means that this angle here must also be 15 degrees. Okay, now that's significant. So let me zoom in a little and fix this a bit. I'll write it a little smaller. So we've just proven to ourselves that this is 15. Okay, now why is that significant? I'm sorry for erasing all these lines. I have to fix that eraser. It's driving me nuts. Okay, that should do it. Yeah, okay. All right, so here's the deal. Why is this important? Why do we need that 15 degrees up there? Well, where's the center of the circle? See, guys, when you're doing a circular motion question, look where the man is. Where's the center of the circle? Well, it's that way. Okay, right now, when he's in this position, it's that way towards the center. So therefore, he must be experiencing a radial acceleration towards the center in that same direction. See, so my acceleration is that way. Okay, that's my radial acceleration. And therefore, my off-axis vector is actually not the force of gravity, which is straight down. It's actually my normal force. Okay, so the normal force will have two components. It'll have one component that'll make blue here, and another component that'll make red here like this. So it's my normal force that is causing, it's actually the blue vector that is causing this acceleration here. Okay, now AY, so this will be my x-axis. My y-axis, we have the vertical acceleration is 0. He's not accelerating upwards or downwards. Okay, now I haven't drawn a very good gravity vector. Let me fix that a little. Okay, I'll make it smaller. That's FG like that. Okay, it's still a little too big, but whatever, it's good enough. Okay, so that's the force of gravity, and this is 15 degrees in there. Okay, so now that we've got this, let's go ahead and do our components and find that minimum speed. All right, so let's do both components. Let's start with the y-axis. We know the answer is going to be on the x-axis, but let's start with the y-axis because there'll be too many unknowns if I start with the x-axis. So let's take a look. The red vector goes with sine of 15, so I'm going to write the net vertical force will equal, I'm going to say up is plus, and the net vertical force is Fn times the sine of 15. That's my red vector, right? And then it's going to be minus the force of gravity. Now this one's 0. So I get, because there's no vertical acceleration, so I end up with that mg equals Fn sine of 15. All right, so that's it so far, okay? Now let's look at the x component. Well, the x component, I'll write over here in the x direction, what do we have? Well, we have the blue vector. So why don't we skip writing Fnet and let's just write MAR. MAR will equal Fn cos of 15, and that is my blue vector here, okay? So now what do I do? Well, now you just go ahead and solve the equations and the unknowns. Now, whenever we have equations in this form, so I'm going to take this equation. Oh, actually, wait. No, yeah, I'll take this equation and I will move it over here. And I'm going to write just underneath this one, actually, can I change my mind? We won't move that equation over there. We'll take this equation and move it over here. So I get mg equals Fn sine of 15. Now our trick is to divide equations in this form. And the mass cancels and the normal force cancels. Good because we don't have either of those things. And I'm left with just one unknown. AR is the unknown over G equals, this time I can't write tan. I could write 1 over tan, I guess, but I'll just leave it as cos 15 over sine 15. Now I can find AR. Okay, so G is 9.8. So I'll take out my calculator. I'll go 15 cos divided by 15 sine equals, and then times 9.8. I get 36.57 meters per second squared. Now that's not my answer, but now to find the speed, I can go v squared over r. Our special circular motion question equals AR, pardon me, AR. So therefore, v squared will equal 36.57 times, and r is 3, so it's going to be times 3. Okay, so let's times this by 3, take the square root. I get 10.5 meters per second. So v is equal to 10.5 meters per second, which is, pretty close to 40 kilometers per hour. Okay, it's like 38 kilometers per hour, somewhere around there. So that's how you do the gravitron ride. See, you see the pattern, right? You just draw the free body diagram, and don't forget our special trick here. We have to make one of the components always the same as the radial acceleration. So that has to be one of the components. So in this case, our x component. The other component will be perpendicular. That's the y component. You need to do that. And the other thing you need to do after that is we use our special formula for the radial acceleration if we need to talk about speed. Okay, that's all. All right, one more example. Okay, and this will help you do the questions on the assignment, I'm hoping. This is a conical pendulum, but it's also a ride at Canada's Wonderland. So here's a ride where it's a rotating swing, okay? Find the period of rotation of the swing. So what they're asking us for is the period. Period is the time for one lap. Now we're going to get that by doing speed equals 2 pi r over t. So therefore, if we can find the speed, 2 pi r is 1 lap. So this is just speed equals distance over time, right? So to get the period, we're going to go 2 pi r divided by speed. So our real goal here is to find the speed. All right, so here you can see the ride, okay, and you see its dimensions. First, we need to find the radius of the circle. Well, the spin axis is right down the middle here. So r is all of this. That's r. Now, how do we find r? Well, you gotta be good with geometry, okay? So we know it's 4 meters from there to there, because look at the top is 8. So we're just gonna split that in half. So it's 4 meters from there to there. But then we have to add to that this little blue thing here because it swings out 30 degrees. Now there's a little right angle triangle here, and this orange rope is the hypotenuse. So, and the hypotenuse is 5 meters long. So that one's going to be, this blue little guy here is going to be 5 sine 30, okay? And 5 sine 30 is just 2.5. So therefore, long story short, therefore, I'll write it over here, r is equal to 4 plus 2.5. Well, that's just 6.5 meters. Well, good, we're partway there. We got r, okay, that's 6.5. Now we just need to find speed. Now to get the speed, we're gonna need to do our free body diagram. It's not, it's not gonna be that, the whole thing won't be that easy. A lot of kids struggled with this question. I put it on a test before. They just couldn't find r, like they couldn't see it. So you have to see that the circular path, goes around like this, right? You have to understand that r goes all the way across there. That's r. And that, if you want r on the other side, this is r on that side, right? That would be r over there. If you can't see it, it's hard to do it, right? So anyway. All right, so now we're getting there. I'm going to draw a free body diagram of our friend right here. Okay, so let's do it. This is, like I said, a conical pendulum. So I'm going to draw the diagram. I'll use black. So let's do it. It's going to be like, here, I'll tilt the object, I guess. There's gravity. There's tension. I mean, it's a conical pendulum. What do you expect? Okay. Now, we do know that this angle here, since this angle is 30 here, we know that that angle is 30, and we need the angle at the base of our vector to properly do components. Okay, now if you are sitting right here, I'll highlight it in yellow. If you're sitting here where the yellow guy is, where's the center of the circle? Well, the center of the circle is to your right. So it's that way, and that has to be your component. So we're going to use x and y components on a normal axis, like oriented horizontally for x and vertically for y, okay? And our radial acceleration towards the center is that way, and this is what all conical pendulums look like. Now I recognize my off-axis vector is the tension. So there is the vertical component of tension, and here is the horizontal component of tension. It's the red vector there that is giving rise to my radial acceleration. It's the red vector that allows that. That's the net force in that direction. And the blue vector is compensating for gravity, okay? So let's go ahead and look at the two components. And this is like broken record, but let's look at it, okay? I'm gonna say up is positive. So the blue vector goes with cos. So you end up, let's just cut to it. We're gonna get that Ft here, gravity, mg, equals Ft cos 30, okay? And then for the x component, that's what we're gonna get. Now I skipped some steps there, but hey, we're pros now. We're getting this, okay? So now what's my red vector? Well, I'm gonna get MAR equals the red vector, which is Ft sine 30, okay? I use my little trick that I used in the previous question, mg equals Ft cos 30. Again, I'm going to divide them. There goes the mass, there goes the tension. Good, because I don't know either one of those things. and I get AR over G. This time equals the tan of theta. Okay, so now what do I do with that? Well, I'm going to find V. So I'm going to solve this for AR. So AR equals G tan 30. So what's AR? Well, calculator comes in, 30 tan times 9.8 equals 5.65 meters per second squared. And this has to equal V squared over R. So V squared over R is 5.65. Now, what do I do with that? Well, solve it for V. So I'm going to multiply that by R, and we already got R is 6.5. We got it up there. So let's multiply by 6.5. Okay, and then take the square root. And I get speed equals 6.06 meters per second. Now I'm going to store that number in memory. Okay, the unrounded number. I rounded that a little. So these are approximate values. Now we go up to our period here. So therefore, our period is equal to 2 pi r over speed. Okay, so that's 2 times pi times 6.5 divided by 6.06. All right, so let's do that. Times 2 times pi times 6.5. And I get 6.73 seconds. I hope I didn't make a mistake. I go fast, so I get 6.73 seconds. And there is my answer to that question from a test. So there you go, guys. Free body diagram, right? And please don't assume like when we were in high school, our teacher goes, here, memorize this formula, okay? Yeah, sometimes it works that way, and sometimes it doesn't. Okay, don't memorize formula that goes with all these scenarios. See, it depends on where the angle is given, right? So if we give you a little twist in it and you don't see that the angle, you won't be the tan of the angle every time, okay, it depends. Like here, we didn't get the tan of the angle, we got the reciprocal of tan, so don't do that. Know how to do the free body diagram, and then anything that comes your way, you can do it. Okay, so there you go. Now, I've got one more thing to show you for today, and all I really wanted to do today was show you different examples of circular motion. So there's one more like that, and I think you're going to like this one. It's not really a roller coaster ride or anything, but it's kind of similar. These are called banked curves. Now look at that bus. Imagine being on that bus. You're probably thinking, how come that bus is not just tipping over right now? Well, because it has enough velocity that its centripetal acceleration prevents it from tipping over, actually. Okay, so if you get the speed right, if it were to stop moving, if it was just sitting there, it would tip. It would absolutely tip over. But if you get the speed right, and in fact, anything faster than that minimum speed, and it will happily stay on the bank without tipping over. Now, I don't know why anyone would do this on a bus, but yeah, I mean, here's a little diagram of the banked road. Now, it looks an awful lot like an inclined plane, and so students get confused. This looks like an inclined plane, but notice how the bus is sort of coming, this bus here is coming towards you, like its headlights are facing you, it's coming towards you, right? So let me erase that little highlight. Okay, and that's what the bus is doing. Now, by the way, we're going to call the banking angle theta. We're going to stick with that notation. But keep in mind, this bus is not just sitting on an incline. It is moving, and it's moving, you know, here in this case, that way or whatever. So it is moving towards you, and it's a three-dimensional problem when you really try to think about it. I've got a little animation I could show you. Hopefully this will work. All right, so here is a car going around a banked curve. Okay, and they're showing you the forces acting on the car, by the way. Okay, the orange vector is not a separate force, it's the net force. There's actually only two forces, the normal force and gravity. They called gravity weight, and that's why it looks like a W, and they called the normal force capital N. And then the net force is labeled the way I would label it. But yeah, that's it. So there you have it, a car going around a banked curve. So keep that image in your mind, okay, when we look at this problem. And again, we're going to ask ourselves a minimum speed problem, just like we did with the roller coaster and the gravitron. And what you're going to find is it's very similar to the gravitron that was spinning around and the guy's back is against the wall. This is very similar to that, except this time the ride isn't spinning around. The car is driving around in a circular path, okay? And so, you know, he's actually moving in a horizontal circle. So let's zoom in on this picture here. He's moving in a horizontal circle. So let me just sketch the free body diagram. And I'm going to tilt my bus. So it's like a similar tilt here. Okay, that's horrible. I'm going to tilt the bus like this. And what forces do I have? Well, I have the force of gravity. I have a normal force. Now, friction would be necessary if the bus goes too fast or too slow, actually. Friction would be necessary to keep the bus from sliding down or up the hill. If you go too fast, it'll slide up the embankment. Okay, it'll actually slide up the embankment. If it goes too slow, it'll slide down the embankment. And if you want to prevent that, you'll require some friction. But let's say he's got exactly the right speed. Well, what is exactly the right speed here? Well, he's moving in a horizontal circle, which is difficult for me to draw, but it's a horizontal circle, which is way, way wide. So here's part of it. And then he's going to go way over there, and then he's going to come back around the curved path, right? So the point being that he's accelerating towards the center of that horizontal circle, which is a horizontal line, okay, off to the left when the bus is in this position here. So I'm going to put my radial acceleration here. And then we see that we're going to need an x-axis that's horizontal, a y-axis that's vertical like this. Now, where does theta fit into this picture? Well, we have to figure it out, okay? So here's where your crazy trig skills come in. I'm going to continue my, oh no, I can't do that. That's not right. Excuse me for a moment while I gather my thoughts here. The ramp is like this, okay? So theta's down here. Okay, so if that's theta, there's a little Z pattern here, so therefore that would be theta up there, but that's still no good to me because I need to figure out how it touches my normal force. So here, let me zoom in a little. This little red angle here and theta in here would have to add up to 90. And this little blue angle here and the red one also add to 90. So what I've just proven is that this blue angle up here is also theta, okay? You gotta see it, okay? You gotta see that geometry there. So that's the banking angle translates up to touch my normal force with the y-axis, okay? So let me draw my y-axis a little better. That's my y-axis. This is my x-axis here. Therefore, the normal force is off-axis, so there's a component like that. There's another component like this, okay? And so now, here, let's keep this one general. Let's not give you any specific numbers. Let's just see how we would work out to find the minimum speed, okay? So first, let's look at the y components. Whoops. Let's look at the y component. And let's cut to it. You're going to get that the normal force times the cos of theta. That's the red vector. So that's this red vector here, right? Equals mg. And in the x direction, you're going to get Fn times the sine of theta equals MAR. Now, once again, it's in our, guys, it's a broken record. So here, I'm gonna go ahead. First, I'll just tell you that's the blue vector, right? So now I'm gonna go ahead and take this equation and write it under there, and you get Fn cos theta equals mg. Divide our two equations, the normal force cancels out, the mass cancels out. like it always does in these questions like this, and you get tan of theta again equals AR over G. And we also know that all we have to do to finish the problem off is we're finding speed, V squared over R equals AR. So it's just a question of plugging in all the numbers. Like I said, our teacher at school made us memorize this thing. It does work sometimes, okay? But if there was friction in the problem, you're done. Whereas you know the method, so you could factor in friction, and I could show you how to do that. But anyway, I digress. We're going to keep it simple for now. So that's how you do bank curves, guys. Pretty straightforward. Now, before I leave you, I did want to talk about flat curves for a second, because here you have to have friction. See, in a bank curve, you can make it around the curve with no friction at all. Okay, like the bobsled, you know, going around the bobsled track, you can get around it with no friction at all. But here, on a flat road, if you want to turn, you have to have friction. In fact, friction is what allows you to turn. So here's a car going around a flat surface. And if you look at the orange vector F is actually the force of static friction. So that orange vector is what's allowing the car to turn in the circle. Yeah, there's a normal, yeah, there's gravity. So there's the normal forces up, gravity's down, they balance out, cancel out. But it's friction, the red vector, that allows you to accelerate towards the center. Okay, so now let's look at how you would do a question like that. Okay, and let me give you a typical question. Let's say the coefficient of friction, static friction, because static friction is the magic friction that lets your car go. Okay, so you drive cars with static friction. Let's say the coefficient between rubber and asphalt is 0.9. This is rubber tires on asphalt. Okay, so my question for you is, what is the maximum speed, okay, you can make let's make it a 12-meter turn radius, all right, for a 12-meter turn. And I want the speed in kilometers per hour, because that's how we drive our cars, right? Kilometers per hour. So a 12-meter turn radius. I'm estimating what a turn radius would be on a typical intersection. Okay, so I'm saying it's around 12 meters. No, I don't think that's too unreasonable, but let's find out. Okay, now the coefficient of static friction is 0.9. So what is the maximum speed? If you take the turn too fast, the tires will start to skid. Now, how fast could you take it so that it wouldn't skid on you? Okay, that's what this question's asking. All right, so let's draw a free body diagram. Now I'm going to draw it kind of like the way the bus looked. And forgive me for this picture. This is my car facing you. That's its headlights, okay? It's not very aerodynamic, I guess. And what it's doing is it's making a left turn. And so from your perspective, the turn is, center of that turn radius is right there, and it is accelerating towards the center of the turn like that, okay? So you're on a horizontal road. Now, if you draw a free body diagram of this scenario, what you get is, here's the car, there's gravity, there's a normal force, and you see the secret is you got to get that force of static friction in there. That's where it is. That's what's allowing you to turn. So this is what's giving you your radial acceleration. Without it, the car will just go in a straight line. You could never turn. You have to have static friction to turn on a flat road. Okay, so now we know that the maximum force of static friction, I'll write it over here, that I can get is mu s times Fn. And from this free body diagram, my y components, I know ay is 0, and hopefully it's 0 when you're driving on a road, right? You're not being launched off the surface. But for the y components, we're going to get Fn equals mg. Let's just cut to it. That's what you're going to get. Okay, so now I'll just go ahead and write mu s mg. Okay, now I'm going to leave it like that. The reason why I'm leaving it like that is because I know mu s and I know g, but I don't know m. So I'm just going to leave it like that for now. And now let's look at the x components on our free body diagram. The x component, there's only one force. The net force equals the force of static friction, right? Okay, so now I go MAR equals the force of static friction, which I'm going to substitute mu s mg like that. Goodbye mass. It's funny how often it cancels out, eh? And we get, I'm going to substitute AR, special formula, v squared over r for radial acceleration. So I get v squared over r equals mu s times g. This is another formula we had to memorize in high school. See where it comes from. See how much better it is to know where things come from and why they come, why they're like this. Okay, so v squared over r equals that. So therefore, v squared equals r times mu s times g. So now I take out my calculator and I know what mu s is and I know what r is. The turning radius is 12 meters. Okay, so that was in the original question, and mu s is 0.9. So I'm going to go 12 times 0.9 times 9.8. I get 105.84. Take the square root. I'm going to get v equals 10.288. I'm going to write 10, won't round it too much just yet, meters per second. Now I'm going to times that by 3.6 to convert it to kilometers per hour, and I get 37 kilometers per hour. Now that's like driving down Jean d'Arc where the speed limit is 40, let's say, in the school zone, and not slowing down at all when you make the turn. If you did that, you could just barely make it. That's what this question is saying. You could barely make it without skidding. But if you kept your speed at 40, you would actually start skidding because it's over 37 as your car tries to make that turn at that speed. But you know, you would naturally slow down. Okay, I hope, when you approach an intersection like that and you're making a 90-degree turn. All right, so there you go. That is the maximum speed. If you go faster than that, your wheels will start to skid, and then you get the static friction will turn into kinetic friction, and the coefficient of kinetic friction will be even less. And therefore, you're going to spin out of your circle to a wider turn radius until the friction gives you enough traction to maintain that particular speed and turn radius. Okay. Now, if you put snow on the road, that will lower the coefficient of friction. So that means this coefficient of friction that you see here is 0.9. Maybe now it's only 0.5. Well, that's going to lower your speed. Otherwise, you're going to slide out of the turn. Okay. You see people doing that all the time when there's a slippery road. All right, guys. I can't think of any more circular motion questions to give you. That's the whole gamut of circular motion questions, with one exception, okay, orbital motion, which that is a lesson unto itself. So I'm going to have to give you that one another time on the next time we do this on Monday, let's say. So then that'll be our last topic. But then we also have a quiz. Okay, so we'll do the quiz on circular motion. Now, if you look at the assignment at this point, and what I mean by the assignment was the circular motion practice page. So if you take a look at that, you can now do all the questions that I highlighted already, including the banked curve. So this one is a banked curve, these guys on the bobsled. And the other ones are universal gravitation. So let's worry about the universal gravitation ones later on. Okay, so I'm leaving a few questions for the gravity, but please try these other questions. I will post answers for you at some point. And that's it, guys. So enjoy your time. This was just a day of examples for you. Okay, so I hope you're enjoying circular motion, and I will talk to you soon. Have a good weekend.